Jeff Dyck was Director of Engineering at Siemens EDA in Saskatchewan, Canada. So he should recognize the backdrop that was on the screen. He's responsible for R&D for 3 software product lines in the Integrated Circuit Verification Solutions division. Prior to joining Siemens, Jeff was VP at Engineering at Solido Design Automation, where he led Solido's R&D teams, managed Solido's product lines, and co-invented Solido's machine learning technologies. Solido was acquired by Siemens in 2017. Jeff is now working on evolving the active learning technology in Solido's products, as well as developing new, disruptively differentiated tools within the Siemens EDA analog mixed signal product line. Thank you very much, Jeff.
All right, and thank you. How's everything looking and sounding? Can you see my screen and hear me and see me okay?
Yes, I can. Thank you.
Beautiful. All right. Hey, well, that's great. Hey, well, thanks a lot for having me, everyone. It's a real pleasure. Back when I started in this space in 2006 in machine learning technologies for EDA, it was a fairly lonely world. There were some optimization folks kicking around that I collaborated with sometimes, but we didn't have a community like this. So it's just amazing to see how this has developed and how much momentum we've got in the space. And really glad to have some more friends around the community. This is amazing. I wanted to talk a little bit about engineering mistakes. You know, there's some mistakes that are fine, right? Some are cute. You know, I went and searched my Google Photos for a goat, and lo and behold, it goes and finds a bunch of goats. And you know, there's this guy here, this terribly horrifying, you know, thing of nightmares lawn gnome that popped up here, and aside from a few nightmares, you know, it didn't really cause any problems. You know, it was just a little error. Who cares? You know, you scroll past it and it found me goats. That's great. But in engineering, errors aren't that cute a lot of the time. This is I work in the semiconductor variation space, trying to help prevent variation problems from happening. And I thought this was kind of a neat story about a not cute problem that Siemens had back in 1874. They were Siemens was actually a pioneer in telegraph technology, and they ran a transatlantic telegraph line. It looked like this is a cross section over here, and there's this variability problem where the outer casing of the telegraph line varied, and it caused it to break. And you know, in true startup style, they said, well, you know, we're going to get really good at patching these things back together. This is Werner von Siemens, the CEO of Siemens in 1874, saying, hey, we went and grabbed this from the bottom of the ocean and fixed it in a day, and this is awesome. But you know, what we're trying to do is prevent these variation problems. They got better at it. You know, future cables that were laid didn't have as much variation. And it's just kind of a cute story, because here I am at Siemens working on variation problems over 100 years later. The ones that we're working on, though, are related to variations in the manufacturing process. So this is a scanning electron microscope image of a FinFET transistor, and you can see there's some imperfections here. You've got some little bubbling and some imperfections in the way that things are shaped, and some of these actually matter in terms of how the electrical performance responds. So things like variance in gate length, if that changes, or fin thickness. This is a FinFET, so it's got fins, and the thickness and the height of those fins affect the electrical properties. The thickness of the oxide layer down below there. Things like that really have a big impact on the electrical performance. And when you put a whole bunch of devices on a chip, millions or billions of them, you know, the worst cases are actually going to be fairly deformed. They're actually quite imperfect. And if those happen in the wrong place, well, it causes chip failure. So that's what we're trying to prevent. Fortunately, foundries model variation, and that helps us a lot with that. But I mean, it's sort of an expensive problem. If you under design, you get yield loss, respin, schedule delays. These are, you know, tens of millions, hundreds of millions kind of problems on a single product. A lot of the time, it's big, expensive problems. And what people do under uncertainty is they'll just go, you know, sort of make things bigger so they vary less, you know, pump some more power so things behave better, turn down the clock, and things tend to behave better. But that's leaving a lot of margin on the table. So you know, foundries model variation. So for example, delta fin height is modeled as, you know, Gaussian distribution. And then you can go and take that and say, well, how's this going to affect my circuit by going and running a bunch of Monte Carlo samples in SPICE and figuring out how your circuit's going to respond to variation. This is what I've been working on for the last 15 years, is products that help with this side of things. So we take in these models, these foundry models from all the major foundries, and there's a whole suite of tools that helps to solve variation problems. And the thing that we did that was kind of different from the rest of the industry, from how other people were looking at it at the time, is we really wanted to accelerate things with any means possible. And at the time, it was just machine learning tools. It was just sort of an implementation detail under the hood. Something that we were using to help. No one really cared until 2016 that we were doing machine learning. Then everyone cared, but it became trendy. But it was just a way that we sped up all of our tools across the board. Part of the secret sauce. And we produced some pretty neat results, some pretty neat benefits. This is from a product called PVTMC Verifier. And what we're doing here is looking at 45 different process voltage and temperature conditions. That's what each of these different curves is here, is a different process voltage and temperature condition. And then we're running out to 4.1 sigma, which would take about 1 million Monte Carlo samples if you were to brute force it out. So about 45 million Monte Carlo samples worth of information here. Perfect answers in the worst cases. And it did it in 1,300 simulations. So, massive speed ups by, instead of brute forcing out this whole space, simulate what you need to, model the rest, and be really smart about it. So that's just a snapshot from Variation Designer. We built another tool suite called Solido Characterization Suite, and this was for creating. If you're familiar with timing analysis, your timer takes in Liberty models, and this is where your Liberty models come from, is characterization. So you run a characterizer, it goes and runs hundreds of millions of simulations and basically produces a big stack of lookup charts with a ton of values in them at different conditions, and that goes into the timer. But there's a whole bunch of problems that get created along the way. It's very hard to verify. That's where analytics comes in. It does a bunch of cool machine learning outlier analysis. And then Generator is actually a pure machine learning tool where it goes and reads in other values from other conditions and automatically produces immediately stuff, new corners, new Liberty files at new corners with no simulation in the loop. So really fast. And it's kind of a slick, easy to use tool as well. Really mature and well developed. The easy part, I think, a lot of the time about machine learning techniques is getting these big speed ups. If you just kind of glance through here, there's a marketing slide. We get lots of 2x speed ups, 10x, 100x, million x speed ups. Huge speed ups, and that's because there's tremendous amount of promise in the whole idea of not simulating everything. If we take the scope of the problem that you actually want to solve and then just really intelligently simulate what's needed, model the rest, you can save tremendous amounts of simulation. The challenge, though, is always about whether you're actually getting the right answer. And that's what the topic of this talk is it's about getting the right answer with machine learning. There's lots of ways to get big speed ups and still get the wrong answer. Doesn't really help that much if the bridge is going to fall or the chip's going to fail. So this is all about getting the right answer. One of the things that I came up with, this is sort of based on how autonomous driving looks at the different levels, or level 2, level 3, level 4 autonomous driving. It's quite popular. A lot of people talking about that. I thought a similar model would be similar for talking about our CAD tools and the way that they use machine learning. So the way that this works is level 0 is no machine learning whatsoever. So this is just, you run everything, and hey, if it works, do it. It's low risk, it works, simple. Often we can't cover the space that we want to cover and the time that we have with the compute resources that we have. So we need to do something better. And that's where the machine learning methods come in, of course. Level 1, what this typically characterizes is something where we've been able to train a model. We can prove that model can interpolate, and actually solve problems within its space that it's trained on. Sometimes we know that, we've trained it on lots of different cases. We throw another case at it, and it works for that case too. So that's cool. We're able to model it. The accuracy is good in some cases. makes for a really cool demo. Sometimes going to be wrong because there are corner cases. This space is quite complicated, and I find that when you change process nodes, or you change even just a sizing on a circuit or something like that, change the layout a little bit, change simulator parameters, even little things. There's just a ton of things that can change. But when things change, the behaviors and responses can sometimes change a lot too. So a lot of these tools that are sometimes right are also sometimes wrong, and it's really hard to know when they're going to be wrong. We can intuit it out on a whiteboard. We can say, well, this will work if the following's true, and then go be surprised at sort of the unknowns. That sort of happens too. So these are neat. These are cool demos. They show promise. They're not necessarily useful for production circuit design because of the fact that they can be wrong and you can't tell. That second part you can't tell is what we thought we'd address first. So level 2 is all about being able to tell. If something's got the right answer, it'd be cool if the tool could tell you, hey, I went and predicted these values from a machine learning model and I verified it for you and the answer is right. And here's how I know. So, prove it. And this is kind of tricky. There's 2 steps here. There's, first of all, deciding what right means, and then also building a self-verifying method that can automatically self-verify predictions. So this is kind of cool. You can actually start using these things in production because you're kind of hedging bets, right? You're saying, hey, let me try the fast machine learning method first. If it works, I'll know it works, and I can take my gains and accelerate my schedule. And if it doesn't work, well, I don't know what to do. I'm not sure. Maybe I can retrain the model. Maybe I can tune some parameters. Maybe I can fiddle with it, try a couple more iterations. Maybe I got to go do it the old-fashioned way. You kind of need a backup plan for these level 2 kinds of tools. You can use them in production because you can tell when they're right, when they're wrong. You're not going to go, tape out a chip that's based on wrong answers. But you do need a backup plan for when you can't get the right answer out. Level 3 is where I think things get really interesting. So the difference between level 2 and level 3 is level 3 machine learning tools they can tell they got the wrong answer. You build a model, I got the wrong answer, and they have ways to recover. So now they can adaptively decide, well, I need some more data, specifically in these areas over here where I know things are weak. I'm going to gather more data, and then I'm going to build a new model on the fly. Maybe I'll even use a different modeling technique, and I have different ones to pick from that I can dynamically, grab data, clean data, build the right kind of model for this, and then re-verify and see if I got the right answer. And this is cool. These are kind of self-healing algorithms. You don't have to hard code in every scenario that might come up. It can kind of just figure them out within and they can start serving a fairly broad spectrum of production cases that you might not have seen before. And the cool thing is, level 2 got us to self-verifying. So, hey, if we've got that, now we can verify and we can fix, right? So it's sort of error detection, error recovery kind of thing at level 3, which is really cool. And then level 4 is the kind of it just works stage. Basically, even if you're level 3, your adaptive approach, there's still corner cases that exist out there. We run into them all the time. We've spent a ton of time trying to handle every single corner case that we've ever seen over the last 15 years. And you eventually get to level 4 is sort of the idea there. This is cool. It just works. Level 3 actually is great though, too, for production. You just need really responsive support. So it almost works all the time. The designer can tell when it's not working. If you've got someone on the other end of the phone that you can call and say, hey, this is busted, and a really responsive team, they can still keep you on your production schedule and solve the corner cases. That's what's really, the other piece that makes level 3 tools work. Level 4, just works. I don't know if anything's really there yet. We're getting pretty close on a couple of our tools, but I don't know if anything is truly level 4 machine learning according to this model. This slide talks about sort of this unfortunate mathematical effort kind of function. Getting from level 0 to level 1. Taking something that we're not using machine learning and showing that machine learning has promise. It works in some cases. That we can do in our team. We bang these off in hours or days. They're pretty quick prototypes that we build up. And that's because we've got people that have been doing this for years. We've got great tools in the toolbox, people that know how to use them, lots of great test data, tons of CPUs in the cluster. We can iterate really quickly through different prototyping ideas to see if something's got promise for solving a new class of machine learning problem, if it's close by to our space that we know well. Level 1 to 2, you have to figure out what accurate means. I'm going to talk about that in a little while. And then making a self-verifying algorithm. This is typically weeks to months of effort, some iteration involved there, and takes a while. Going from level 2 to 3, where we're actually making this all dynamic, you got to go build your data acquisition tool, cleaning, dynamic model building. This is trickier stuff, so it takes sort of months to years to do this kind of thing. And then level 3 to 4, this is we're still working on. It's years to decades to get there to really get something to a level 4 machine learning tool. So the point here is that each level is about an order of magnitude more work, and what we really need to do in order to get things that work really well in production is get at least to level 3 with great support. I find that that's where things start to scale and lots of people can pick up your tools and use them, depend on them. And then level 4 is even better. Level 2 is kind of tricky in that you have to define what the right answer is first. It's sort of a self-verifying step, but to do that, you have to know what right means. And right is tricky to define for an engineering problem. I heard a couple questions in previous sessions about, are you sure that the interesting answer isn't the max difference? There's sort of questions, like, I don't know, it sort of depends on the problem, right? So you have to really understand your context and your domain. We talk to designers about their tolerances. A lot of the time, they don't need a perfect answer. There's a bit of noise anyway in the way that things are modeled and a bit of room. So if you can have a bit of a tolerance, that allows you to sometimes use that to speed things up more, or actually build a technology that wouldn't work if it had to be perfect. Sometimes you look at these in terms of relative or absolutes. There's conditional tolerances. If low voltage, do something different than high voltage in terms of tolerances. They take a while to figure out. Acceptable error rates is tricky too. Sometimes people say, well, I can't have any errors. And sometimes you've got millions of values and you're willing to, if you can get 1000x speed up, it's okay if some of them are a little bit out, as long as they're not out past a certain amount. You sort of figure, well, that's a good trade-off. There's also regions of interest. A lot of the time we don't care about all cases. So, case of gain on an op amp in a previous talk here. With gain on an op amp, you care about the worst case gain. You don't really care about the ones in the middle and the highest gain. You care about worst cases typically. So, defining regions of interest and targeting those is going to be important. So defining right is sort of trickier than it sounds. Designing an algorithm that can tell when machine learning results are right is also kind of tricky. What I start with usually is I get on a whiteboard with someone who knows how they would probably prove that this is right. What would you do if you had to manually prove that this algorithm didn't screw up? Sort of a brute force method. Well, if the brute force is too expensive, we're not going to do that. Can we do some, space fill sampling? Can we check regions of interest a little bit more? Can we do, look at our machine learning models and see, where it thinks things are least accurate, go and simulate in there and see how far off we actually are. Those are good methods. I personally like things that are designed as self-verifying algorithms. Self-verifying algorithms by design. I'm going to show an example of that in a little bit, but if you can actually design an algorithm that does this part, you don't have to go and sort of do it as a post-processing step that's, hopefully good enough, but still debatable. If you can actually build a self-verifying algorithm by design, that's even better. So this is, getting to level 2, kind of the hard parts, then you go build that. Level 3, the way that we do this is we have this this flow that we tend to use for a lot of our tools, and I'll just go through how it works. I've talked about this before, so if you've seen it, please bear with me. But we start with a design of experiments. You start by simulating a small amount of the total space. Then you build your machine learning model, your very first generation of machine learning model. So I've got some data, I build a machine learning model. I go and predict the rest of the space with this machine learning model. Then now I know where my areas of interest are, because I know what the output space looks like based on the predictions from the model, and I can start saying, hey, let's go dive into these areas of interest, or worst cases, or achieving a certain level of accuracy throughout the whole space, or something. You based on what you defined as your accuracy criteria, you target stuff that's going to help you get there. And then what you do is you take that data that you've just gathered in these areas of interest, and this is where this starts getting cool, is you go back and you build a new model with that data. So now you've got more resolution in areas of interest in your model. You can go do a couple of iterations of this. You can also say, well, let's go look at where there are the biggest inflections in output space, maybe, areas where there's a lot of inaccuracy because of the action that we're seeing in output space. Like sometimes we'll see, temperature inversions happen. You want to find that vertex where the temperature inversion's happening, add some more data there. Sometimes there's a low voltage drop off in performance. You want to find that elbow where the low voltage drop off's happening, and do some more simulation in there. And you can then go and take that and again, build another model, do an iteration or two of that. And now we've got a model that's actually getting pretty good. It's got an idea of what the whole space looks like. It's got high resolution areas of interest. It's got high resolution in areas where there's action in the output space. And we can say, hey, well, now let's go throw this into our self-verification step and see if we can prove that we got the right answer here. If not, you can take the data that you got from self-verification and go back and rinse and repeat some of these other steps to further add more resolution, get toward the accuracy you're targeting. So this is actually a pretty resilient model. If you think about this compared to just, training a model and then seeing if it works, and then, manually sort of trying to figure out what to do, this is remarkably better. And it can solve all kinds of problems that we haven't seen before. That's the real power of this. So this is what level 3 active learning is from our perspective. It's sort of the algorithm we use in a lot of our tools. I just wanted to talk about one of well, I think this is the first level 3 machine learning tool that I know of in our direct space. This is one that we invented in 2008 called High Sigma Monte Carlo. And I talk about this one quite a bit because it's kind of an elegant solution, really demonstrates well what this level 3 concept's all about. So the challenge here is that Monte Carlo and SPICE accurate high sigma analysis takes a lot of simulation. As you go up each half sigma, it takes about an order of magnitude more simulations to get to another half sigma. So if you're trying to target 6 sigma, you're looking at 10 billion simulations. Obviously can't brute force that out. Lots of tricks out there for trying to get out there. A lot of them can be wrong in some cases. So goal here, of course, is we want to get out to 6 sigma, but we've only got maybe thousands of simulations in our budget. And we built this. This is actually a screenshot from the tool circa 2008 when it was in beta. It was a fairly early looking tool with some widgets that I can't believe existed. But you can see it's beta here. It actually, it could only get out to 5 sigma or something like that. It was fairly limited. But it was really cool. It could actually get out into the tails, and it could prove that it got the right answer, and it could adaptively go and improve the information in its tails and solve problems it hadn't seen before, and solve corner cases that would normally take another iteration with a developer. It could automatically do that, which was really quite neat. The way that it worked is, if you kind of look at Monte Carlo sampling, if you just brute force it out, you do billion samples, they just randomly come in. This is what we don't want to do. But the idea here is, what if we could just automatically know where the tail is and start simulating in from the tail here, and say, well, hey, I'm just going to run these 10 samples. This is all I really need to do to get to my 6 sigma point. My 10th point is about 6 sigma in a billion, or 10 billion samples, I should say. And so we can actually just start running in from the tail, which is really neat. Take the 10th worst one and not have to run everything else. That's sort of the perfect scenario. What actually happens in practice, I'm just going to skip through some of this stuff. What actually happens in practice is it's not perfect, right? We go and build an ordering model. We simulate these in what we think is the order. but it's not perfect. And you can see that there's some that are out of order there. But the cool thing about it is we can see it's working. It's not simulating things through the middle of this distribution. Everything's toward this end here. And, even if it's a little bit out of order, we can just kind of power through it. We've got thousands of simulations for a budget, so we could run quite a few of these, even if they're out of order, and just keep running until the amount of error that we're seeing that's causing the error in the ordering is less than the margin that we've created to the actual Six Sigma point, and then stop. So this is one of those accurate by design, self-verifying by design type algorithms where you can see it working. It can tell it's working. It can tell when it's not working. When it's not working, it can go and say, hey, I need to go and add more data. I need to build another model, different kind of model, try some different things. But it can actually do generations of adding simulation and rebuilding models and simulating in from the tail in what it thinks is the order until it gets the right answer, which is really cool. And it was especially really cool in 2008 when no one else could do this. There were other tools that produced an answer, but no one could trust them. Our previous tries actually were like that too. You couldn't trust them because you couldn't see them working. They couldn't prove that they worked well. And this tool was the first one of its kind that actually could prove that it worked well. It sort of went from level 2 to level 3, well, level 1 to level 2 to level 3, and most other things that people were using were level 1 at the time. So that's High Sigma Monte Carlo, and we've been working, actually, the reason why I like talking about this one is we've done a ton of work over the last, I guess it's been 13 years now, ton of work to try to get from that level 3 to level 4, where it feels like we just kind of, for a long time worked on making it more broadly applicable, more general. Can it solve this problem? No. Okay, let's go, change that. So, massively increase the capacity, million samples to 1 trillion samples, actually many trillion. It's unlimited now, technically. We went from 1,000 process variables to handling, it's now hundreds of thousands of process variables that it can handle. So orders of magnitude increase in what it can handle. It went from being able to handle continuous outputs only to being able to handle multimodal distributions, which are tricky, especially if you don't know they exist. Binary, trinary type distributions to pass-fail type outputs. Can handle anything, which is really quite cool. Could only handle one failure region in input space. Now it can handle any number of failure regions in input space and so on. And it does it all automatically, which is really neat. And we've handled a lot of corner cases. It hasn't been just we built more features and added capacity. We looked and we said every time it couldn't find the right answer, the cool thing was, well, it knows it's got the wrong answer, so we can address it, which is one of the really good things about level 2 is now you can, if you know you've got a problem, well, you can go and fix it. But we actually were able to, fix a lot of these things over the last 13 years by being fairly relentless, and made a tool that is pretty close to the it just works promise of level 4. Very, very rare that we have any issues with this tool, and it's used in very large scale across, it's 22 of the top 25 semiconductor companies use this product now. So I wanted to talk about getting to level 4. What kinds of problems do we actually see and solve? And I just went and asked our team. I've got 120 software developers on my team, and good chunk of them work on machine learning corner cases for a living. And I went and asked them, what have you been working on for the last few months? And I got 3 really, really neat projects that I just wanted to share with you. The first one is jagged waveforms. So waveforms are hard to model. Jagged waveforms are really hard to model. And we had Scott Johnston, James Marquez, Ken DeLathwer, and Megan Marsh that were working on this one. And this problem's really cool, actually. So waveforms are shapes. This is basically showing a whole family of waveforms across different voltages. Each one of these different colors is a different voltage. And this is actually a power waveform. That's why it's jagged. These power waveforms tend to be really jagged. You can see these kind of sawtooths in here and sharp angles. And we had a great waveform modeling method for the time domain. Doesn't work very well here. We're getting atrocious accuracy on some cases. So they dug into it and they said, well, if you plot this out and look at it, you can see how it kind of, the shapes across different voltage, they kind of accordion in and out, and the main characteristics of the shapes stay about the same. Like you can see this little sawtooth repeating here. You can see that it's just kind of, getting stretched out over voltage. So different voltages, it's getting kind of stretched over the time domain. And can we actually model some of the features? We can't model the shape directly. We tried. That was a non-starter completely, but can we actually model some of the attributes of this and actually model these waveforms? Now, we did this before. This is how we did our time domain stuff as well. And the features that we picked, the attributes that we picked from these waveforms didn't actually work very well in the power domain. So this is just showing, how this works. You can kind of, what are these parameters of a waveform? Well, you can take max value, min value, median time, max time. You can sort of take these, extract these parameters and lots more, right? There's lots of ways of parameterizing a shape. And then the idea was that, if we just plot every one of them and just see which ones model best, can we use those to go and morph the shape and then reconstruct it? So we started with, this is one that we were using for the time domain, absolute area. And you can see absolute area across voltage here is super jagged, right? Maybe you could draw a linear model through that, or maybe a bit of a quadratic or something, but it's still going to be really inaccurate just because the actual raw data is super inaccurate. Oh, it's not inaccurate, this is exactly accurate, it's just really noisy. So it's really hard to model across this space. So there's a problem. You're going to get error if you're morphing these based on a model of absolute area. That's not going to work so well. If you look at actual area, not absolute area, but area, it's much cleaner. You can see it's almost a linear response, which is cool. We didn't know. Had to look at it to find out. Median time's another one. We used this one before. You can see it's a little bit noisy, not too bad. Kind of a nice quadratic, can almost fit that with some error. But if you look at, instead of median time, you look at mid-area time, which is take the midpoint of the area of the waveform and look at the time there. This one actually, for whatever reason, we didn't even look at the theory behind it. We just looked at the behaviors. This one actually models really, really well. So the cool thing is, if you pick the right parameters and if they can actually be used to morph those waveforms, well, you pick parameters that you can model really effectively and then apply those to the way that we're morphing the shapes. Well, what we end up with is a remarkable improvement. We went from 80% intolerance. That means 20% of the answers were wrong from our customer's perspective, which is a disaster. 80% in the typical case, 50% at the worst case corner. This is horrible. It means half the answers are wrong, to almost perfect, just by picking the right parameters to build models across such that we could properly morph these waveforms. So kind of a cool problem. It's one of those level 3 to level 4. And we could detect that we got the wrong answer. We went and dug under the hood and we figured out why we were getting the wrong answer, handled yet another corner case, and now it's a little bit more robust and just works for jagged waveforms like we see in the power domain. This is another one. It's a high sigma adaptive correction for vector sampling error on nonlinear corner cases. And this is Joel Cooper, who I've known for 20 years. I met him tree planting in the bush in the 90s, and Matthew Voigt, and they handle a lot of our hard algorithmic problems. Just a quick primer on what vector sampling is. If you kind of look at input space, we've got a statistical distribution, which is Gaussian distribution. And if we go sample this, if we go run 3,000 Monte Carlo samples on this, and plotted an output space, we get from about -3 sigma to +3 sigma. We cover that -3 to +3 range. If you take that same distribution, you just kind of squish it down. We call that scaling, or adding a vector factor to it. We scale this out, sort of squish it down. Well, then what happens in output space is it actually spreads out further, and then you can correct for the spread, but it actually spreads out further, and you get out to maybe -4, 4.5 to +4.5, squish it even further, you get out even further in output space, so -6 to +6. And don't think that you can just take this method and it solves high sigma problems. The confidence intervals get wider as you get as you squish more. So it's a way to get quick and dirty answers out at high sigma, not to get a perfect answer, but it's useful for fast estimates. It's often first phase of an analysis for us or something, kind of a screener test or something, or something just to see if you're even in the right ballpark. Now, what this is supposed to do is, as you scale, the sigma of your chip is supposed to stay the same. It should, right? Like you're squishing the input distribution, you're seeing what it looks like in output space, and it should still be the same chip sigma. And this holds every time we'd ever seen. We've been doing this for like over a decade, and it held really, really consistently all over the place. Then we ran into this really weird case here. Actually, I've got a better slide for this. So we ran into this really weird case here where we knew we had the wrong answer from this vector sampling. It was giving us a very, very high sigma for a case that was like, it was off by orders of magnitude. It was like a 5.4 sigma case, and it was reporting back at like 6.8 sigma. And it's like, how does that happen? Well, let's see what happens if we change the scale factor. So we ran another one, and the sigma dropped. It should be about the same with a little bit of statistical noise. It should be about the same. It dropped. And we ran another one, and it dropped again. And it's like, well, what's causing that? It turns out if you've got a case that has lots of failure regions in input space with a very similar probability of occurrence, you get this really unfortunate response to vector sampling. And we didn't know this before. We knew that there were some cases where it would overshoot and we would correct for it in other ways, but we didn't know why it was happening. Finally figured it out. So we figured out a new way to solve this. What we do is we take a worst case statistical point, or basically our wrong answer, and we run it at a bunch of different scales. So run a bunch of different scales up until the point where we see, these are outliers, and they happen because we're actually not generating, we're not scaling enough to find failures in this case. So this is a binary output, so you can kind of like ignore those ones. So we filter those out and then build a model through this nice linear model, boom. And we can actually scale back now to a scale of 1, and that's our answer. We can actually use this to correct, and it just takes a handful of simulations. So now we've got a way of correcting all these for all these crazy cases. So pretty interesting. And the last one I was going to show is one that James Cooper just did. It's multi-finger devices with very few simulations. So problem that we have here is multi-finger device. We ended up with 512 process variables, of which there were 64 of them that were significant. So our effective dimension, I should say, was 64, which is a pretty high effective dimension. We only had 200 samples to work with, which is really lean for an effective dimension of 64. And this caused huge problems. So the green line here is the right answer. Yellow is what we were getting. And we knew it was the wrong answer. The tool detected it. That's good. But why was it happening? What can we do about it? Well, and this produced terrible outliers. You can see all these ones that are outside the green tolerances here. These are all ones where our customers look at it and say, I can't use this tool. This is the wrong answer in production. So cool, but not what we want. Anyway, the solution for this one, to keep the number of simulations, well, we could just crank up the number of simulations. If you use 3,000 simulations, you get the right answer, but we didn't want to go and run 15 times more simulations. So the observation here that James made is the devices in a multi-finger device, they're nearly identical, their effects are nearly identical. And so all we need to do, we can keep all the variables, we can keep them varying independently, but just use common basis function coefficients between devices, which actually takes this down to an effective dimension of 2. And with just 200 simulations, we get a perfect answer. So neat trick, and it works just on multi-finger devices, but it's a way of speeding those up tremendously. So what I was trying to show with these three is level 3 to 4 is hard. There's lots of corner cases in the space. It takes lots of work and ingenuity, I think, to work on those and get through that. This level model, I think, is really effective because it really helps us to understand what we've got so far. If we've got a partially reliable solution, well, we know we need to level up. We need to define what accurate means and make it self-verifying, and probably make it adaptive before it can really be used significantly in production. For most, at least the cases in my space, that's true pretty much across the board. And then that struggle to get to level 4, I mean, you better have great support because it's going to take a while to get to level 4. That's kind of the the message there, but it's worth trying, and definitely helps a lot with the quality of the tools. Again, order of magnitude more effort to go between levels, which is an unfortunate scaling factor, but it's really important. Good to know what we're up against. And good to know about how much work it takes to get something to that kind of level 3 where it starts to be getting interesting for production, I think. And if there's one takeaway from this, it's really that levels 3 and 4 are useful for production engineering applications. Leveling up's hard, it takes a lot of time. You have to do it if you want tools to be production relevant. And there are a ton of great research problems remaining in going from level 2 to level 3 to level 4. And I think that's the good news for us is it's going to keep us busy for many decades to come. That's it for me. Thanks very much.
Thank you very much, Jeff. Thanks, it's very interesting. Are there any questions, please? I have one. Tesla claims will get to level 4 because they have massive amounts of customer data, because everyone gives up their privacy when they buy a Tesla. Will you need massive amounts of customer data to get to level 4? And if so, how will you get that?
Yes is the answer. So just the first thing about Tesla is I think, part of what they're doing is they're not really addressing the corner cases like I talk about here. And I've been saying since 2018 that they're not going to achieve level 4 the way that they've approached it. They're trying to, and I've been right so far. They've been saying, oh, it's going to be next week or whatever. It never really happens, and they're way off. They're not even close. And it's absolutely true that you do need a bunch of real world data. I was telling my dad, he was saying, well, how come I have a Tesla? I appreciate the effort, I bought one. And my dad said, well, how come the self-driving doesn't work very good? And I said, well, think about this. We were going to his house, we were driving to his house, and he lives on a little bit of grid road with some rough patches. And I said, just no one got this corner case and said, well, what do you do when there's corduroy on a gravel road? Do you slow down? Do you move over to the no one programmed that part, right? No one said, well, let's take that and program something that solves that yet. And it's sort of a game of many, many corner cases, I think, to get there. And the whole Tesla self-driving core, I think, is only 300,000 lines of code or something. There's going to be tens of millions or hundreds of millions of lines of code to handle these corner cases, is what I think. So anyway, that's you triggered me there. I got a rant about Tesla and the approach there. But for us, we've actually taken a different tack where we have gotten lots of customer data. The way that we get it is by having great support and a great relationship with our customers. There's only thousands of users that we have. That's actually a lot of circuit designers. It's thousands of users. And when they have a problem, they call us, we find out about it, we go solve it with them, and we actually do get lots of customer data. So we've got the benefit of 15 years of interacting with real world production customers. Some of them give us things in house. We've got VPN connections into 17 of the top semiconductor companies where we can actually go there and run regression tests and stuff in their environment on stuff that's not allowed out. So we've built that over a long time. And I guess I should have just said yes. That you do need lots of data, and that's how we've been getting there. It's really important, and it's one of the hardest things in this industry.
Thank you. Thanks, Jeff. There's a question online. Have you, in your years of experience, noticed more frequent and faster jumps going from level 1 to level 2 or 3, given the amount of interest in learning going on currently? Has it become easier to get more support across teams?
Yeah, this is a fantastic question. What I see a lot of is people achieving level 1 and declaring victory, right? This is the end. This is all we need to do. It works in the lab. It makes for a great demo, but it doesn't work in production. And having been there and taken that to customers, this is what we did, more times than I want to admit. You sort of take something, they say, well, how do I know this is going to work on my kid? Well, it's better than nothing, isn't it? And they say, no, it's worse than nothing because I can't tell if it worked or not. I'm not going to go bet my design on this. So I see a lot of people in the space, and I think it's great. It's sort of identifying opportunities is the way I look at it. It's sort of a way of identifying opportunities. So, they're developing all these level 1 solutions, but then they're not following through. And I've seen very few level 2 and level 3 solutions in our space emerge. And I think that's why, in production, I think machine learning is still a bit of a disappointment, right? It was the big promise of 2018. All the big companies in the space were going to pour in a ton of resources, and chips were going to design themselves, and it hasn't really happened yet that much. There's been some shining stars, but there's a lot of stuff that's stuck at level 1, and people are just figuring out that that's not good enough. So I think the interest needs to shift to getting to level 2 and level 3. And that's why I laid it out this way, is hopefully it gives a framework for people to understand what they have and where they need to go for it to be useful in production.
Great. Let's see if there's any more questions.
I have a question, Paul. Jeff, first, great talk. And you described the framework of active learning, minor sampling, then sampling again in the area of interest. So whenever you do active learning, you need a way to balance the exploration exploitation.
Yes.
Can you share some of your experience in how did you handle it?
Yeah, I think you always have to start by exploring. If you have nothing, you have to start exploring, because there's nothing to exploit yet. You can use some cool like rules of thumb to decide, well, hey, I'm gonna, like one thing that we do in high sigma Monte Carlo is we want to build a high sigma model. So we go generate billions of Monte Carlo samples. Then we take the ones that are farthest from nominal in multi-dimensional input space. And we say, well, let's start by exploring there. So it's a little bit exploitive. It's mostly just exploring. But once we've built our first model, then we can actually get into exploiting mode, right? So we start to know what the responses look like. We start to know where the areas of interest are. It's the resolutions there. And that first iteration, that first generation between when we've explored, built a model, now we can go and really pinpoint. So I go straight to exploitation after that first model build generation. You explore, build a model, and then it's exploit. Because if you're still exploring, it means that you probably didn't do a good job in your first stage of your design of experiments. You can go back to that and run more if it's just sort of still a mess, still a hazy mess. You can do that. But the ideal situation, I think, is you've got a good enough design of experiments initially. You get your exploration done, build your model, and then you're really targeting things that are a lot more meaningful based on what the model's telling you. So it's explore first, then exploit intelligently till you're done is typically how they play out in practice for us.
Thanks. This is, I think that it makes sense with something that we are playing with. So this is very interesting answer. Thanks.
Awesome.
And another question. So there are, for some of the problems that you described, there are non-machine learning or other prediction or optimization algorithms that are being used in the industry and have shown some good results. Can you say something about a hybrid approach, or will you find it valuable, or will you find it something that it's better to take a different approach and attack the problems with from a machine learning point of view?
I might have missed part of the question. So you're asking, are you asking, are there completely different approach? Because I think I know what you're saying, that if you're looking at for example, how can I design a schematic for something that's better with more of a generative design approach or something like it's quite different than what I described here. Is that what you're sort of asking? Are there completely different approaches than what I described, and how do you find them? Is that the right question? Or
so even before, let me rephrase myself. So even before machine learning, there were approaches to make it better than complete random.
Oh yeah,
or exploring the entire space.
Yes.
So either way to take the good of both worlds. or when it is the right approach in your experience to say, okay, let's keep it aside and try to learn from scratch in a sense.
So yeah, I totally understand what you're saying now. So, you know, the way I've historically looked at this is I never tried to take machine learning methods and use them to solve a problem. I'd start with the problem and see, well, what tools do we have in the toolbox to help? And a lot of the time problems are solved without using machine learning at all. And you know, I showed one example in there that was vector sampling, right? So vector sampling, that is not a machine learning technique, but it can get us out into our tails. And so that's a useful one. I talked about design of experiments. This is not a machine learning technique. This is just a really structured way of saying, you know, how should we explore a space? So I think you know, if you take the machine learning toolbox and look at it as just a bunch of tools for solving a problem, and you take every other tool that you've got, you know, you sort of build a big toolbox that's not just machine learning tools, a whole bunch of things, and then really fall in love with the problem, not the tools. You know, fall in love with solving the problem, not with using the tools. You're going to produce much better solutions because not everything is best solved with a machine learning solution. And if you actually look under the hood, if I was to go and say, you know, what percentage of tricks in the Solido tool suite are machine learning tools versus something that wouldn't be classified as machine learning, it's probably like 1/3 machine learning, 2/3 not, you know, in practice, something like that.
Thanks. This makes perfectly sense to me.
Yeah, it's a good question. I think that sometimes because of the trendiness of machine learning, everyone wants to cast things as a machine learning problem. Sometimes it's not, you know. So, well, I mean, it can be, but sometimes better solved in a different way.
Well, thanks very much, Jeff. Thanks so much for a very interesting talk.
Yeah, it was my pleasure. Thanks a lot for having me.